The broadcast is now starting. All attendees are in listen-only mode.
Good day, this is Fiona from the FEKO marketing team, and I would like to welcome everyone to this webinar today. Dr. Ulrich Jakobus will be presenting on the topic HPC usage in FEKO. A recording of the presentation will be available within 24 hours, and a notification email will be sent to you providing a link to the presentation. We encourage you to post questions for Ulrich throughout this presentation in the area provided on the right-hand side of your screen. You don't have to wait until the end of the presentation to post your question, but Ulrich will probably only answer them at the end of the session if time allows. For further information on FEKO, please visit our website or contact your local distributor. You are also welcome to contact us via the email address that appears at the end of the presentation, webinars@emss.co.za. I will now hand over to Ulrich, and we hope that you enjoy our presentation.
Thank you very much, Fiona, for this introduction. Welcome everybody also from my side. I'm Ulrich Jakobus, the FEKO product manager, and I would like to talk today a bit about the high-performance computing options which FEKO offers. As outline of my agenda, I am going to start actually with an item to illustrate that for the solution of many practical problems with FEKO, one doesn't really need high-performance resources, large computing clusters due to the different methods and solvers we have in FEKO. But even those, in some cases, one might want to do cross-validations and so forth. So we offer a number of options in the HPC environment. The first one I would like to discuss is our parallelization strategy of the different solvers for both distributed and shared memory like multicore environments. We also will cover a bit the CPU support, GPU computing that FEKO offers, and then look at some other features related to HPC such as farming, related to our optimization engine, remote launching, or the integration into queuing system and workload management systems. We offer also inside of FEKO support and integration into some external HPC solutions that I'm going to present. And at the end we'll discuss some of our licensing options supporting the usage of FEKO in HPC environments. Let me start with the first chapter, which is devoted to showing how the usage of HPC in FEKO could be avoided, or at least could be pushed to a point where the problems are really large. Many of you might know that FEKO is not only a single technology, a single solver algorithm, but it's rather a suite of codes based on different solution methods. We have the traditional, let me call it almost brute force method, full wave solvers, like method of moments or finite element method. And we are going to add in FEKO Suite 7.0, which is going to be released end of May, also a finite difference time domain method. And these solvers are based on a rigorous meshing of 2D or 3D space, and related to that is a certain scaling of memory requirement and runtime, and HPC comes into play to make these solutions possible. We have traditionally followed, in addition to supporting HPC, another approach where we try to develop intelligent algorithms and solvers which can cope with complicated large-scale problems using small computers, little memory, so trying to counter the growth of the problems at a pace that is much faster than the growth of computing power over the last years. You will see now some examples how that is possible. And in addition to these different methods, we combine them in a hybrid way, so different methods can be used to solve the same problem in a fully coupled environment. And we also offer some special solutions which, if not available, would also require very fine meshing, large number of unknowns, but with certain approximations which are valid in certain ranges, one can reduce the computational effort quite a lot. So let me start by looking at a standard boundary integral equation solution using full wave method of moments. Also there, by using intelligent algorithms, one can reduce memory and runtime drastically, avoiding the usage of HPC. You see here a radar cross-section calculation of a ship using at the top a standard lambda over 10 mesh, resulting in about 43,000 unknowns. We have at the bottom shown the same solution using higher order basis functions within the method of moments framework. You see at the bottom the mesh, at the top the mesh is so dense you can hardly see it, it's just all a gray blackish area. The number of unknowns gets reduced here by a factor of almost 6, which for the full wave method of moments, which is used here, translates into a saving in memory requirement by the square of that number. So it's about 32 times less memory, and in the result graph you see the green and the blue curve for the radar cross-section, that they are nearly identical. The next example I would like to briefly cover is the replacement of the traditional method of moments by a faster integral equation solver, the multilevel fast multiple method, which we have released already back in 2004, which reduces the computational complexity from order n to the power of 3, where n being the number of unknowns, to a n log square n formula, and similar for the memory requirement, this gets reduced from a square dependency to n log n. And this is what I mentioned earlier, much faster, the savings are much faster than any growth in the computer power could achieve. You see here an example of a similar ship that we have seen just now, computing now here 10 parameters at a higher frequency, and using the traditional method of moments, this memory would need 1,500 terabyte, and an estimate for the solution time is about 1,090 years on a single core, single CPU machine. So of course, having now say a 10,000 core cluster with enough memory might make it feasible. On the other hand, by using just intelligent solvers, which for this problem are as accurate as the full wave method of moments, we can get that down the scaling as shown in the previous slide, and we can easily solve that problem on a single computer, 66 gigabyte memory, and the runtime is 1.9 hours. So it's a huge, huge difference. Going beyond the multi-level fast multi-method, if the problems get larger and larger, also this method, due to its n log n scaling, still has a growing requirement for memory and runtime. This is where the high-frequency asymptotic solvers in FEKO kick in. We solve here a large reflector antenna. The multi-level fast multipole solution, our fast integral equation solver, uses about 5 gigabyte of memory and runs about 2 hours. So it's quite practical, but if the problem gets larger, that will grow, or if you think about doing optimization runs, a 2-hour runtime might not be desirable. On the high-frequency side, FEKO offers, for instance, here the physical optics or the large element physical optics, or our shooting and bouncing ray solvers, the ray launching geometrical optics. And you see that for these two, the last two, the memory is about 1 or 2 megabytes, and not gigabyte, megabyte, and the runtime is far less than a minute. And the results you see at the bottom, left and right comparison with the near field for that particular problem. That's also excellent agreement. We went even further in our new release, FEKO Suite 7.0, and there will be a webinar the 30th of April introducing the new features. We have combined the iterative, in an iterative way, the multi-level fast multiple method with physical optics or large element physical optics, with the full bidirectional coupling of the two methods. So it's not solving two different problems, it's one single problem. And you see here a similar reflector antenna with a horn and a sub-reflector. We compare a full MLFMM solution using 12 gigabyte and less than 1 hour to the new hybrid MLFMM large element physical optics using about 300 megabyte. And at the top, the results, you see excellent agreement of the far-field radiation pattern, and only at about 60-70 dB below the main radiation, one can see some small differences on the left and right hand side. And lastly, I mentioned in the introduction, FEKO not only offers these different methods and the hybrid combination of those. In FEKO we also have very specific solution methods for certain practical problems, like for instance windscreen antennas. This is a challenging problem because the glass where these antennas are embedded consists typically of multiple layers which are extremely thin, and in a traditional way, using for instance finite element method or finite different time domain, these have to be discretized each layer, which causes quite an increase in memory and runtime. We offer very efficient special solution techniques within the method of moments or multiple method to address those efficiently. And you see here a comparison at the top, a rigorous full wave finite element method of moments solution where the various glass layers are discretized, and at the bottom our efficient windscreen model. The top shows the results compared to measurement in blue, windscreen analysis in red for the S11 input impedance, and at the bottom you see also again a huge saving we can achieve from 1.8 gigabyte memory down to 250 megabyte, and runtime from about 7 minutes to less than 3 minutes. And the last example is for arrays. Often one solves large arrays of, for instance, your horn antennas or patch antennas or whatever, Vivaldi antennas. And also the number of elements in the arrays has a strong impact on the overall requirements regarding memory and runtime. We also implemented here fast solvers. We call it the domain Green's function method, DGFM, and you see already for that simple example with only 5 elements in the array, we are able to reduce the runtime from 1.5 hours to half an hour, and in particular the saving is evident in the memory from about 7.5 gigabyte down to 320 megabytes. So why have I explained all that? I think it was there. I had two purposes of this introduction and overview of the fast solvers. Firstly, to illustrate that it is not always necessary to use full wave brute force methods or large computers, large clusters to solve electromagnetic problems. With the intelligent choice of different solvers and their hybrid combinations, it is well possible to get useful results on standard workstations with a certain memory requirement. Of course, we understand that in many cases one has to use a multi-level fast multiple method, for instance, if it's a high-frequency scattering problem with complicated materials where multiple reflections are important, internal resonances and so forth, and the high-frequency methods cannot be used. And this is why we have been supporting from the very beginning of FEKO HPC solutions through parallelisation, GPU support and so forth, as I will be discussing in the following. I just want to highlight a challenge that we face. Because FEKO is not a single algorithm, we have all these different solution methods. We have the hybrid combinations of those. These different solution methods itself are broken up into different phases. For instance, for the method of moments, we have the phase of matrix fill, matrix solve, near field, far field calculations, and all of those need to be addressed, of course, efficiently to avoid any bottlenecks in an HPC environment. And this is also one of the reasons why we historically support MPI-based parallelization for distributed memory systems for all our solvers, all our algorithms. The newer technologies like shared memory parallelization using OpenMP or GPU support are phased in and are not yet available for all the solvers and all the phases, as you will see and as I will illustrate now. Let me start with the first aspect of HPC, and this is the parallelization, support for multi-core systems, for multi-CPU systems, and in particular for cluster-type environments. And as I mentioned just now, FEKO has traditionally always been available in a parallel version based on MPI, the message passing interface, supporting large clusters, but at the same time also supporting multi-core environments through shared memory communication. What is important, however, is that each of the parallel processes can only see its own memory space. This is no problem at all for the method of moments. We can ideally split the matrix. There's no overhead, there's no duplication, except for some specific geometry information and some material parameters, or the frequency must be known, of course, to all the parallel processes. For the MLFMM in particular, which is also typically used by our customers in these large parallel environments, there is a kind of a compromise between communication and keeping certain data local, and we have implemented a specific strategy to keep certain arrays related to the transfer functions in the MLFMM local, and this is why you see later in examples that the memory does not scale ideally. To avoid that, at least in environments where one can indeed access the memory from different processes or threads, we added about 3.5 years ago in FEKO Suite 6.0 our shared memory parallelization based on OpenMP for certain algorithms. And quite important, and of course, is a hybrid parallelization strategy where we combine the usage of MPI for the communication between the nodes of a cluster with OpenMP for the parallelization inside of the different cores or CPUs hosted on the same physical machine. The activation of that is quite straightforward. I'm going to illustrate first how to do that in the user interface. It's typically done by a machines file, which is either available separately or in our GUI can be defined in a table. Here we specify, for instance, we want to use 2 nodes in a cluster with 2 processes each. And by starting the run by default, it would launch 4 MPI processes, 2 on node 1, 2 on node 2. But by checking the checkbox, use shared memory / OpenMP threading for multiple CPU nodes, multiple CPUs, just by activating the checkbox, we switch to the hybrid parallel model where we would launch 1 process on node 2 and 1 process on node 1. But each process is then spawning 2 threads under the OpenMP programming model. For command line usage or within queuing systems and scripts and so forth, it's also very simple. We have the traditional run FEKO as our launcher command that you will see a few times here in this presentation, followed by the file name, number of processes, machines file, and by just adding the option --use OpenMP threading, we are switching to a model where we use then, instead of MPI, the OpenMP for the processes running on the same node, physical node. And note, however, again what I said initially, OpenMP and GPU have been phased in only gradually over the last 3 years for the different solvers where we think it is useful. In particular, for instance, you will see MLFMM where we have a certain duplication of memory if we use multiple processes. Certain solvers, like for instance physical optics, UTD, ray launching, geometrical optics, we don't have that OpenMP option yet, and it also doesn't really offer that much advantage over MPI. Let's look at an example, ideal, small, academic example. We solve a method of moments problem with about 25,000 unknowns on a system with 2 quad-core CPUs. We look at the speed up, which is the factor by which a parallel run runs faster as compared to a sequential run. And in the ideal world, you will get the black line, which means if you use 2 cores, you would expect double the speed. If you use 8 cores, the speed should be 1/8, or the speed should be 8 times faster and the runtime 1/8. If we use MPI for all the communication between all these processes, you see the red line, and say for the largest run done here with 8 cores, we get the speed up of about 6. By switching to OpenMP, this not only has the advantage then for MLFMM to be more memory efficient, we also see here a specific speed advantage in this example, about a factor 7 the speed up for 8 cores. For a practical problem, what does that mean? How does that speed example translate? Here again a very small, simple example, but it's already big enough to illustrate this effect. Method of moments, again about 25,000 unknowns. That's now not using higher order basis functions, also that's basically a brute force method. We use a cluster with 6 nodes, each node equipped with a dual core CPU, and we compare 2 different models of running that solution. The first one is using 12 MPI processes, and the second one is using 6 MPI processes, 1 on each of the nodes, and then each of them using 2 threads. So we will have 12 threads in all these situations, and you see here from the runtime, indeed what we saw already with the previous example is confirmed. It goes down from 426 seconds to 377 seconds. For the MLFMM, as I already mentioned, we have intentionally implemented a certain local caching of certain transfer arrays for the MLFMM transfer function calculation to avoid too much communication going back and forth all the time. So it's a kind of compromise between memory and runtime. And by switching to a hybrid MPI, OpenMP shared memory model, you see here at the top that not only the runtime reduces, but also in the bottom in particular the overall memory requirement, so that the peak memory of all the processes added together can be reduced by about 25%. We have also spent some effort, even though the parallelization, in particular of the method of moments in FEKO, is quite old. We even did that before MPI was introduced as a standard, still with the RPC parallel framework, remote procedure calls. We are continuously optimizing it, and this is a very extreme example. It's a smallish problem solved on a cluster with too many nodes. And at some stage, the communication overhead will just kill any performance, and we have intentionally not used the InfiniBand connect of that cluster. We have rather used the backbone connection, the 100 megabit per second Ethernet, which has a low bandwidth, high latency, to overemphasize these effects. And what you then see here is if we use about more than 20 parallel processes on that particular high latency, low bandwidth network, the communication overhead will kill any parallel scaling and the runtime will actually increase. We have implemented optimizations in changing the parallel process grid layout and so forth in our FEKO Suite 6.3 release last year to get a much better scaling in this case as indicated by the red line. Moving back to the multi-level fast multiple method, you saw the earlier motivation with the ship that instead of 1,000 years we can solve it in about 2 hours. Also there it's quite a challenge to get it parallelized efficiently with the different phases of the solution process, and in particular we, or rather our customers, solve very general problems. These can be open problems where one has to use a specific type of integral equation, the electric field integral equation, and in order to get a solution, preconditioning is an absolute must. And there's quite a challenge in getting robust and stable preconditioners and parallelizing them efficiently. And you see here the result that we have achieved for a ship model with about 3.2 million unknowns. And you see here again the efficiency, the parallel scaling. 100% means perfect scaling, so if you use 32 parallel processes, the runtime will be reduced by a factor of 32 if we had 100%. And you see here we are getting around 80, 90%, maybe up to about 20 parallel processes, and there onwards close to 80%. And given the challenges of how this method works, I think that's an excellent result. And also there we have been doing some improvements and continuously look at other ways of parallelizing the preconditioning. And we have made an extension now also in our latest release, FEKO Suite 6.3, in October last year, where we added another parallel preconditioning option to our finite element and multi-level fast multiple solutions, which allows, firstly, gives better scaling of the memory, and secondly, also has an out-of-core option, which sometimes if the run is too large, and especially once you enter the preconditioning phase, we have already allocated other arrays for the sparse near-field matrix, for instance. It might have been in the past that your run was just too big to fit your specific cluster or computer. With the out-of-core, it's possible. We see here the total memory requirement of all the parallel processes added together as a function of the number of parallel processes. Again, it's a very small run, just to illustrate this effect, up to 10. And ideally, of course, and this you would see, for instance, for the method of moments, the memory remains constant. The more processes we add, the more the memory is subdivided into the different processes, and the memory requirement per process is reduced. For the MLFMM, as already indicated earlier, as a kind of a compromise between runtime and memory requirement, we keep certain arrays local. So this is why you see here an increase in memory. It's not, of course, linear. So if you go from 2 to 10, so you increase your number of parallel processes by a factor of 5. We don't use 5 times more memory. It's here just, say, 7, 7.5. A factor 5 would be around 38. We are at about 10.5 maybe, and this is caused by the overlaps. You see now the new result in FEKO Suite 6.3. We use less memory, and quite attractive is the new out-of-core option, which is represented by the black bars, where we can then get a solution with much less installed main memory. And then in parallel it's swapped out. Every process is using its own stretch file. But interesting, I haven't shown it here, the increase in runtime is within a few percent. Let me move on from the parallelization strategies and some example around the parallel version of FEKO for distributed and shared memory environments to GPU accelerations, graphical processing unit. It has become very popular based on the NVIDIA devices, which are based on the CUDA programming language, and now others are coming up like OpenCL. And as illustrated earlier, these devices consist of hundreds of cores internally, and not all the algorithms in FEKO lend themselves to an efficient implementation within the GPU environment. We have made available so far those where we think it is very useful and where there is a real benefit, which are in particular the linear algebra functions in FEKO, like the method of moments, matrix operations, the LU-decomposition in particular, backward substitution, the eigenvalue solver for our characteristic mode analysis. Other phases are work in progress, like for instance the relaunching of our relaunching geometrical optics solver, or certain other algorithms like, for instance, the method of moments matrix fill. The activation is again very simple, very straightforward. In our user interface, it's a bit small here, in the Run Launch panel, there's a very small arrow here in the corner. Clicking on there opens the component launch dialog, and there on the FEKO tab there's a checkbox, use GPU, and we automatically detect, of course, if you don't have a supported GPU with the necessary NVIDIA CUDA drivers, we will give a warning and fall back to the regular CPU usage. From the command line, if it is used from scripts or queuing systems and so forth, it's just adding the -- use GPU command line option to the run FEKO core. And it's also, by the way, safe. You can add that option, you can keep it on permanently. If you then use, for instance, physical optics, which is not enabled on the GPU yet, we will also just automatically switch back to a CPU version. Or within our hybrid framework, we would use the GPU for one of the solvers and use the CPU for the others. Here an example of the performance gain that one can achieve, and it's a bit like comparing apples and bananas. One is comparing different things. We compare, say here, one specific CPU, an Intel Core i7-2600 with 4 cores, so we run on all the 4 cores, and compare it to a NVIDIA Tesla C2070 graphics card. We use the method of moment solver with the matrix algebra executed on the GPU with a varying number of unknowns from 2000 to 20,000, and plot here the performance, the measured performance in gigaflops, so this billion floating point operations per second. For the quad-core CPU, we enter quite soon at about 10,000 unknowns into a steady state performance of about 150 gigaflop. When using GPU support, our first version where we introduced that FEKO Suite 6.1 was leveling at about 600 gigaflop, so that's about 4 times more than this quad-core run. By certain improvements, we were able to push that limit in FEKO Suite 6.2 a bit upwards. We are around at about 700 gigaflop, and in FEKO Suite 6.2 we also added support to use multiple GPUs within the same run from the same process or thread, and this is represented here in the green graph, and you see also for the larger problem sizes we almost double the performance. Leaving the area of GPU computing, I'm going to move on to some other high-performance computing features that we offer in FEKO. The first one being the support of the latest technology that the CPUs as such offer. For instance, as example, I have selected here AVX, the Advanced Vector Extensions, which is an extension of all the SSE instruction set of the CPUs that was proposed back in 2008, and it was only in early 2011 when Intel and AMD released the first CPUs supporting that instruction set, and we have followed in FEKO. Initially we wanted to have it ready when the CPUs got released, but there were some technical issues, so we were holding it back by 1 year, but in September 2012 we released AVX support in FEKO with different code branches. So of course if you have a CPU not supporting that instruction set, FEKO, the same binary, will still run, but you then use an alternative code path. And here a benchmark problem, we have tested the method of moments with about 30,000 unknowns, comparing the previous version, FEKO Suite 6.0, without AVX support to FEKO Suite 6.2, where we solve exactly the same problem on exactly the same computer. In this case, it's not even parallel, it's just sequential to isolate this effect. using the AVX instruction set, and you see that we can increase the speed almost by a factor of 2 just by adding support for that. As part of HPC support, it is of course essential to integrate with job scheduling and workload management systems that are used to manage large HPC facilities through our use of Intel MPI, which is a default MPI that actually ships with and installs with FEKO in its runtime environment. We integrate into a number of queuing systems. You see here the list, and this is automatically detected by run FEKO. So all you have to do is you call the run FEKO and the file name, and then you append the option --use job scheduler, and FEKO will then detect if it is run within a queuing system. It will detect within which of these queuing systems it is running, and it will obtain all the necessary information like how many jobs to launch in parallel on which nodes and so forth from the queuing system. Of course, one can still launch traditionally. If you are within PBS, for instance, you can use run FEKO file name -n $PBS nodes and so forth, and refer to the machines file. That's also possible. We also have a graphical component which is called QFEKO, which together with certain scripts on the cluster allows an easier usage of remote facilities and clusters to avoid, for instance, that you upload all your files to a cluster, launch a job, come back after the weekend only to see an error message that some include file was missing that you forgot to copy. QFEKO will take over that task and find any dependencies of include files that are required, will pack all those together in an archive, optionally allows even encrypting this archive with a public key of the cluster, transfers this to the cluster, sets up the queuing system script with the parameters which are defined in the GUI. Once the run is finished, it could, by the script running on the cluster, be again package all the results together using a public key from the user so that the results remain confidential and cannot be seen by any other one, and convert them or transfer them back. We also, if it is an interactive run, so not interacting through queuing systems, if you have, for instance, a desktop computer and have a powerful workstation somewhere else where you have interactive access, we have an option in FEKO to remotely launch runs on another machine, either sequentially or launch parallel runs. This is accomplished by just firstly configuring it with the host name and then defining whether SSH or MPI-based solution should be used, and then by activating in the Run Launch panel the remote button. Remote launching will be active, or from a script with the --remote host option specifying then the IP address or the host name. And this also takes care of automatically copying the files back and forth, launching the remote run, and in particular one can interactively monitor and see the progress and the standard out exactly if it was a local run. There's no real difference. And the last aspect of the other HPC offerings we have, I would like to mention here in this webinar, is within our optimizer. We have, in addition to supporting, of course, parallel runs and GPU computing and so forth, all that I explained so far, we have the option of so-called farming. And farming means the concurrent solution of different optimization steps or different configurations during the optimization on different computers, different nodes of a clusters, or even just different cores of a multi-core environment. And this can, of course, be combined with parallel processing. So we can do farming and farm out, for instance, parallel runs while the optimization is running. We support that with our grid search optimization technique, which essentially is a parameter sweep and with the particle swarm and genetic algorithms, where one run doesn't necessarily rely on the history and result of the previous run. You see here an example. I've used a horn antenna, which is optimized for gain, very simple academic example, and we use here the particle swarm optimization using farming versus sequential on a 6-core machine. For the sequential run, for instance, this algorithm chooses a population size of 20 and has, after 15 iterations, reached the termination criterion, and we get about 17.08 dB gain, and it runs in total, in this case with that many generations, about 3 hours. Using farming, automatically the algorithm decides that the population size should be a multiple of the number of farming hosts, in this case 6, so it's using 24. It terminates then after 12 iterations, and we see here that the total time instead of 3 hours is about 0.35 hours, so it's roughly about 10 times faster. And interesting also is we have implemented load balancing in that algorithm, because not every optimization run will take the same time. If we change the parameters of that horn, some horn antennas might be smaller, other might be larger, and then it takes longer to solve those. And this is what happens here. You see here the number of these 6 farming options, the number of cores, and you see here, for instance, due to the load balancing, the first core solved, and my apologies, that's a bit small, about 40 of these configurations, and the others solved about 50. Let me move on to the next topic, and this is how we integrate into other or with other HPC environments. What you have seen so far is all what we natively support in FEKO. We don't need to use any external solutions, any external service providers. We just need to have the appropriate FEKO license, and I will cover that just now. Regarding external solutions, I've selected a few. The first one I would like to mention here and highlight is CrunchYard, which is a kind of a simulation on demand service offering hardware. You see here, for instance, I've just taken it from their website. They are not the biggest, real big clusters that some of our customers have, but at least for certain occasional users who maybe have only a few 100 gigabyte or 100 gigabyte machine or even smaller, and occasionally want to use big runs, that might be an attractive option. One can just sign up on the website, register. Upon registration, as part of a trial, there's actually an allocation of some free credits, so it's free of charge. And what is interesting and really attractive here, we have installed FEKO on CrunchYard, and there is an agreement in place where the usage fee that you pay per core hour covers actually the FEKO license as well. So you don't just rent time and then have to install your own FEKO license in order to use it. It's part of the package. There's a company in Italy, NICE, and they offer desktop cloud visualization software, and we also support this, and it has been tested. And the primary goal here is similar to what I've shown earlier, the remote launching, to make it easy for a local user to submit jobs to a remote data center, initiate there the parallel runs, integrate with the queuing systems, get the results back, and in particular also visualize the results, monitor this while one is on the road with a laptop computer, quickly log in with maybe not a fast interconnect, and still be able to influence the runs or even share results and data with someone else outside the organization. Some of the features are summarized here. I think the emphasis in particular is on fast graphical rendering on the data center and then just transferring images across to a user who might have a low-end machine like a tablet, and offering these type of solutions. It has been announced in December that we as company EMSS with FEKO will merge with or will be acquired by Altair Engineering, and Altair has great HPC facilities and infrastructure tools which are listed here on that side, like Compute Manager, Display Manager, very similar offering than the nice DCF solution shown in the previous slide. Altair also owns and develops and maintains PBS, the portable batch system that we have already integration with, as you saw from the slide, with the Intel MPI supported queuing systems, and there's PBS analytics to analyze all the data and accounting and so forth. And through our merger activities, where we are not yet maybe at the level of the highest level of integration, we will certainly address all those and offer a much tighter integrated usage of FEKO within that Altair PBX Works suite of HPC tools. The last slide in that area of our external collaborations and interfaces and so forth, I would like just to mention 2 certifications that we are doing on a regular basis in order to ensure that FEKO works with and is ready for HPC environments. The first one is the Intel Cluster Ready program, which brings together hardware and software vendors to a specific standard that once there is a certified hardware under the Intel Cluster Ready program, we as distributors and developers of FEKO, once we have gone through that certification, can more or less guarantee that FEKO as Intel Cluster Ready certified software component will work seamlessly on an Intel Cluster Ready certified hardware system. And in a similar light with Microsoft, we certify on a regular basis our FEKO installations and binaries and so forth, and can then claim that we are Windows HPC server ready. Let me discuss, or let me say a few words regarding the licensing and the options we have to be able to use all those features that I've presented so far. In general, we have different categories of our pricing. We have a free version aiming mostly at students or the occasional home user, which is called FEKO Lite. Unfortunately, it will not support the HPC features that we have discussed so far. It's also limited in problem size, and it wouldn't make sense to use clusters or GPU support. The standard CPUs and the single CPU are fast enough, and the memory is also limited. Quite attractive, I think, for the audience of this webinar is our evaluation license, which is available completely free of charge for 45 days, offering all the features. And even if you are already an existing user of FEKO and are maybe tempted now through that webinar to try parallel versions on clusters, you are very welcome to contact your local reseller and ask for an evaluation version for a specific cluster and so forth. And then our regular licenses are either purchased or rental licenses, where we have 4 different pricing categories. We have bronze, silver, gold, and platinum. Bronze and silver being limited in memory, gold being unlimited 64-bit or 32-bit on various systems, Windows and Linux, and this is, I think, the most popular license these days. Traditionally, we still support platinum licenses, for instance, on the SGR Altix machines running Intel Iterative or the older IBM RISC and Solaris, ICHES, but they are being phased out and we haven't made any sale of those. And existing customers with those are also welcome, of course, to contact our resellers and ask for conversion of platinum into gold. to save on future license and maintenance fees. Of particular interest within that HPC webinar is that our parallel licensing scheme counts the number of sockets or CPUs, and we give you as our users all the cores within one socket for free. This also means if you have a sequential license of FEKO, sequential in that context means it's for one CPU, you can still run parallel processes with a sequential license supporting all the cores you have in your CPU. We have implemented that, and that was a change. Earlier we used to charge per process. We implemented that change to accommodate the trend in CPU technology to not increase anymore the clock rates as it used to be still 10 years ago, but to rather go add more computing power by increasing the number of cores. Our parallel pricing is also quite attractive. It's not that a 2 CPU parallel license is double the price as compared to a sequential license, or if we go for instance from 64 to 128. It's a highly nonlinear, attractive pricing model. The GPU computing that I've illustrated is completely free of charge. If you have a FEKO license, you can check that checkbox. You don't have to pay anything extra. And to accommodate and encourage using of high HPC facilities, we have the option to buy a larger license, like for instance gold, for such an HPC environment, and then access it from various clients using a cheaper GUI-only version, which includes the full pre- and post environments and a reduced kernel. And we also introduced for such environments about 2 years ago a premium floating license option, which allows a single license to be split into the user interface and kernel components. The split could be for 2 different users, or in particular here in this background of HPC, it could be 2 different machines. So you could use from one single license the kernel components on a big number cruncher and the associated user interface at the same time on another computer to do the pre- and post-processing. With this slide, let me conclude this webinar by summarizing again some of the key aspects. I have shown in the introduction that by being such a versatile tool, having so many different solvers, we actually push the boundary when HPC is required in FEKO to really large problems. We have fast solvers, asymptotic methods, hybrid method, special solution options, where often it is not necessary to use HPC for the solution of a given problem. When one well needs to involve larger computing power, I have shown you the various parallelization options of FEKO using MPI for distributed memory environments, which can also be used for shared memory systems, and then the specific extensions we have made in the last 3 or 4 years with OpenMP and a hybrid shared distributed memory model. I have covered the GPU aspects for the certain solvers that we are supporting. I have touched on the integrations into job scheduling systems, remote launching, the farming for the optimization, the remote visualizations through NICE, DCF or Altair's PBS works in future. I have now in the last slide discussed some of our pricing options applicable to HPC. And just as a future outlook, of course this never stops. There will be new features released, like for instance Intel Xeon Phi that we are currently busy with to look at. We are continuing to expand our GPU support for other solution phases. I mentioned the ray launching geometry optics as an example, and then also already mentioned a tighter integration into PBS works from Altair through our merger. This concludes then this webinar, and you're welcome to type any questions or comments that you might have into the comment field. Let me see if there are already some questions. There is a question I see, which is the Windows job scheduler the same as the Windows HPC cluster? I'm not so familiar with what the term Windows HPC cluster, but I believe, the Windows HPC only ships with one built-in job scheduler, and I believe this is the same. I'm seeing no other questions coming through. You are of course welcome to ask questions also at a later stage. You have the contact details on the webinar registration form, or contact your local reseller. I would like then to thank all of you for your attention. We hope that this webinar was interesting. You have learned new things, and have a good day further.